Welcome back. And today I would like to share a little bit more about the curvature and also something about the velocity and the acceleration of a motion. Now, first, I want to introduce about the concept of radius of curvature. Um, so this is a curve, and at one point, we can actually use a circle to approximate its curvature, and it has a curvature, so we want to find the radius of that curvature. So basically what we want to do is to find the relationship between the radius of the circle and the curvature of the circle, because I want at that point the curvature of the circle is equal to the curvature of the curve. So for a circle with radius of r, what is curvature? Let's write its expression first. Let's assume the circle is x is equal to r times cosine theta, and y is equal to r times sine theta, while z is equal to 0. So this is a circle on a plane of z equal to 0. Then the expression of the vector function is r cosine theta, r sine theta, and 0. This is a proof of one of the formula. And then we know that r prime of t is equal to negative r sine theta, r cosine theta, 0. R double prime is t equals to negative r sine theta, negative r cosine theta, negative r sine theta, and 0. So, and also the magnitude of the r prime is equal to r. By the formula, the curvature of t is equal to r prime times cross r double prime magnitude divided by r prime to the power of 3, the 1, 2, 3 rule. So it is equal to those two cross product, I, j, k, negative r sine, r cosine, 0, negative r cosine, negative r sine, 0. After dividing that, you will figure out that it is actually equal to r squared. It's 0, 0, r squared. So the magnitude of that is r squared, and it is divided by r to the power of 3. So it is equal to 1 over r. Therefore, we know that the curvature is actually equal to the 1 over the radius. Wow, so we find a really good relationship between them. Imagine that what curvature means. The curvature means that if it is a straight line, it is 0, means that you don't change, and it is really sharp, change extremely fast. Here it is approaching infinity. What about the radius? Well, if you think that if you stand on a point and it is a straight line, it is actually a circle with a radius of infinity. So the approach is infinity. While at here, if it is so sharp enough, you will find that the circle that fit is actually r equal to 0. So that fits our formula. Therefore, we know that r is equal to the 1 over the curvature as well. Now, let's move on to another topic, which is the tangential and normal component of acceleration, which I mentioned before yesterday. And someone asked me about how to prove it rigorously. So this is the proof. This is an excerpt from our textbook. The acceleration is actually, if we write v as this, the nu is the magnitude of the velocity, and t is the directional vector of the velocity, and a is actually equal to the derivative of v, which is this one, using the product rule, lefty right and righty left. So we know that this is the parallel component, and this is the perpendicular component. We know that the t prime, since the t is a unit vector, how it changes must be perpendicular to its direction. So this is normal to t. So finally, we can derive a sentence like this from the pure mathematical proof. However, this has a physical explanation. How do we do that? Well, first, I want to try to use this formula to form a physical explanation of that. A is equal to the nu prime t plus k nu squared n. And we know that the curvature is actually 1 over r, so it is nu prime t plus nu squared divided by r times n. Wait a second, what is this? We know that in a circular motion, the acceleration, the centripetal acceleration is equal to the v squared divided by r. Wait, this is exactly the acceleration of pointing towards the center of the circle in this formula. And what is this? This is how it changes the velocity. So imagine if you are on a point of a curve, you have a velocity like this, and you also have a acceleration like this. It has two components. One is parallel to the velocity, and the other is perpendicular to the velocity. We know that we will know that the parallel component will change the velocity, magnitude of the velocity, or nu. So it looks like this. And the perpendicular component will not change that, but it will provide it to do a circular motion. If we have a acceleration like this, it will provide a centripetal force that make the particle do the circular motion with the radius of r. Therefore, we can treat this moment at that point as a circular motion with the radius of r. And r, we call that the radius of curvature. So, right now, we can treat every single movement as a combination of infinite circular motions. At every point, we can treat it as a little part of the circular motion. Therefore, this is the famous circular motion theory on the normal I think. So this time, we use the mathematical method to prove that this theory is correct. So this is the special note on the velocity and acceleration. Hope you liked it, and